Hello everyone, welcome to the third part of the tutorial on nonconvex optimization. Today I'm going to talk about spectral method, and this is an outline for this part of the tutorial. We will begin with a motivating application on community detection. Then, based on this application, we will extract a general recipe for spectral method. We will then apply this general recipe to at least two more applications to get familiar with this spectral method. To understand the statistical performance of spectral method, we further introduce two types of analysis. One is called classical spectral analysis, which provides Euclidean distance bounds on the perturbations, and the other is called, I call it fine-grained analysis, which provides L infinity norm perturbation bounds for the spectral methods. In the end, we will conclude with a bird's eye view of the possible extensions, including things we don't have time to talk about in this tutorial. Now, let me directly jump to the first part, the motivating application, community detection. We know that community structures are common in many social networks, whether it's a friendship network or co-authorship network. The goal of community detection is to partition the users into several clusters based on their friendship similarity graphs. To understand this type of similarity or friendship graph data we have, we need to first have a statistical model to explain this data generating process. A handy model is called stochastic block model, in which there are n nodes to be classified, and we assume there are two communities for simplicity. We have n unknown variables, x star 1 all the way to x star n, to denote the community membership. In particular, we use 1 to denote the fact that this node belongs to the first community, and we use -1 to denote the membership of the second community. What we observe in reality is often a graph G, and in SBM, it assumes the following. A pair of indices ij belongs to the graph G with probability p if I and j come from the same community, and with probability q if they are not. Okay. Here, oftentimes p is assumed to be larger than q. That's because in practice, people have similar background, or people belonging to the same community tend to be connected more often. The goal of community detection is then to recover the community memberships of all the nodes based on the observed graph G. Okay. Equivalently, the data we have can be written as an adjacency matrix A, where Aij equals to 1 if and only if edge ij belongs to the graph. Okay. Without loss of generality, from now on, we will assume that the first half of the nodes belong to the first community, and the second half belong to the other community. And that just means x star 1 to x star m over 2 is equal to 1, while the remaining entries are equal to -1. Okay, so given such an adjacency data we have, how shall we proceed to classify the nodes into two different communities? It turns out that it is helpful to look at the expected version of this adjacency matrix under the SBM model. If you actually calculate the expected version of this adjacency matrix, you will find out that expectation of A is just a rank 2 matrix, shown here. And you will soon notice that the first eigenvector is kind of uninformative. It is the all 1 vector. However, the second eigenvector, 1 minus 1 vector, is quite informative, and it is exactly equal to the community membership vector x star we are seeking. Okay, so based on this calculation, it is intuitive to come up with the following spectral clustering method, where we first can compute the leading eigenvector u of the shifted adjacency matrix. So we just shift the adjacency matrix by an amount of p plus q over 2. And in the second step, given such an eigenvector, we output xi to be 1 if ui is positive, and we output xi to be -1 if ui is negative. This procedure is also called rounding, so we classify the nodes based on the sign of the eigenvector. The rationale behind this method is quite simple, as we just explained. The recovery is reliable if the size of the difference between A and its expected version is sufficiently small. In the extreme case where there is no difference between A and its expectation, we know from the previous slide that the leading eigenvector U of A will be proportional to the eigenvector 1 minus 1, which will perfectly cluster all the nodes in the graph. Okay. So this finished our introduction or the motivating application of community detection. Now we want to extract a general recipe for spectral method using this application. It turns out that based on our prior experience, there are three key steps involved in spectral method. First, we need to identify a key matrix M star, whose eigenvectors disclose crucial information about the quantity of interest. Okay. And in the second step, in view of this key matrix M star, we want to construct a surrogate matrix M using the data available. Okay. We want M to be as close to M star as possible. In the end, we just compute the corresponding eigenvectors of this surrogate matrix M. Now, let's apply this general recipe to two more applications. The first one should be familiar to you by now. It's called low-rank matrix completion, and it has been introduced in the previous parts of the tutorial. In this problem, we have an unknown low-rank matrix M star, whose singular value decomposition is given by U star, sigma star, V star transpose. And for matrix completion, what we observe are just partial entries of this matrix. We further assume that each entry M star ij is observed independently with certain probability P. Okay? An intermediate goal in this problem is to estimate the leading singular spaces U star and V star of the matrix M star. Okay? To address this problem, how shall we use spectral method? We can follow the general recipe. First, we identify the key matrix M star here. Okay? In this problem, the key matrix M star is quite simple since we are estimating it and its singular space will reveal the information we are after. And in the second step, we construct a surrogate matrix M using the data we have. It turns out that we can construct it as follows. We set Mij to be 1 over P times M star ij. If M star ij, this entry is observed, okay? If not, we simply set it to be 0. Okay, so you may view it as just one scaled version of the observed matrix we have. The rationale behind this rescaling process is to ensure that the expected version of M matrix is exactly equal to the M star matrix, to the key matrix we identified. In the end, we just compute the rank R SVD, use sigma V transpose of this surrogate matrix, and use that as our estimate. Okay, so this is how we apply the general recipe of spectral method to the problem of matrix completion. Let's try another one called ranking from pairwise comparisons. It is not uncommon to find pairwise comparisons in our daily life. For instance, to rank tennis players, we often have pairwise matches or pairwise comparisons between them. And then based on these pairwise comparisons, we want to rank all the tennis players, okay, in the pool. Again, to illustrate or to understand the data, the pairwise data we have in reality, we need to have a statistical model to explain the data generating process. Here is a traditional one called Bradley-Terry-Lewis model. And suppose you want to rank n items, the BTL model will assign a latent score, W star I, to each of the items, so that operationally speaking, item I is preferred over item J if and only if the score of item I, W star I, is larger than the score of J, W star J. Okay? And with such a score in hand, BTL postulates the following fact, that the probability of item J beats item I is governed by the ratio between W star J and the sum of W star I plus W star J. as you can see from this formula, probability formula here, you will soon see that a larger W star J, say if W star J is larger than W star I, then item J has a higher probability, over half, to beat item I. That means item J is preferred over item I. Okay, so given such an underlying statistical model, the data we have, the Bernoulli random variables Yj we have, we will use Yij equal 1 to denote the fact that J beats I, and 0 if otherwise. Okay, so such a Bernoulli random variable will follow the BTL model. That means Yj equal to 1 with probability equal to W star J divided by W star I plus W star J. The ultimate goal in this problem is to rank the items. However, as we said that the order of this score vector review the ranking of the items. So an intermediate goal is to estimate such a score vector W star. Here I put up to scaling because, as you can see here, if you arbitrarily multiply W star by a positive constant, it will not change the statistical nature of this problem. So we only need to estimate this score vector W star up to an order or up to a scaling. So similarly, how shall we apply spectral method to address this problem? We will follow our general recipe. First, we want to identify a key matrix whose eigenvalue structure or eigenstructure will review the information we are after. So it turns out that here we can construct a probability transition matrix P star, whose off-diagonal entries P star ij is equal to 1 over n times the key probability we just introduced. And for the diagonal entries, we simply set it such that the row sum is equal to 1 for every row. Okay, that makes it a probability transition matrix or a stochastic matrix. The rationale behind this identification or construction of this P star matrix is as follows. First, P star as a probability transition matrix satisfies a condition called detailed balanced condition. It just means that there exists one vector W star such that if you multiply the ith entry of W star by P star ij, it is equal to if it is equal to W star j times the P star j I entry. Okay. Once a stochastic matrix or transition matrix satisfies this detailed balanced condition, we know from the theory of Markov chain that the stationary distribution pi star of this Markov chain P star, or in other words, in the linear algebra sense, the leading left eigenvector pi star of this matrix P star will just be the normalized vector of this W star. Okay, so pi star is just W star divided by the sum of all the entries in W star. Okay, so as you can see from this simple calculation that the leading left eigenvector P star review the score vector we are seeking. Okay, given such information, we can then move to the second step where we construct a surrogate matrix P using the data we have. So we can simply put the off-diagonal entries to be 1 over n times Yij and put the diagonal entries similarly to make it a probability transition matrix. You can check that under the expectation. That means the expected version of this P matrix is exactly the P star matrix we just introduced. So in the end, in the last step, we just return the leading left eigenvector pi of this P matrix as the score estimate. It turns out that this spectral ranking algorithm is closely related to the PageRank algorithm Google has been using in their search engine. Okay. Having applied this general recipe to at least 3 applications, we soon identified that the key to understand the performance of spectral method is to understand the stability of the eigenspace or eigenvector against the perturbation. Okay, we want to say something like the following. If M is quite close to M star, so the surrogate matrix is quite close to the key matrix we construct, we want to say something like the following. Their eigenvectors are also quite close. Okay? That's the key in understanding the statistical performance of spectral method. So to understand this, we first introduce the classical spectral analysis, the L2 perturbation theory. And before we formally state the theorem or the perturbation bounds, let me give you a bit setup and notation. We will consider two symmetric matrices M star and its perturbed version M. Here M is just a superposition of the true matrix M star and the symmetric noise matrix E. They will have the eigen decomposition as follows, okay? And you can see here that I group a bunch of eigenvectors together. To be more specific, I will group R eigenvectors together and name them as U star. For the remaining ones, I call them U star perpendicular. I will apply the same grouping strategy to the eigenvalues and call them lambda star and lambda star perpendicular. Okay, that's the eigen decomposition of the key matrix M star. Similarly, we have a decomposition for the surrogate matrix M. It's perturbed version. The main focus of eigenspace perturbations theory is to understand how does the perturbation E affect the distance between U and U star. Okay. Before we answer this question, there is actually another more basic question. That is, how should we define the distance between two subspaces? Okay. We know that it's quite trivial to see that the Frobenius norm or the operator norm, the spectral norm, are not appropriate to use in this regard, since they fall short of accounting for the orthonormal transformation in subspaces. That is, for any orthonormal matrix R, the two subspaces represented by U and U star are actually the same subspace. So there should be zero distance between U and UR. However, this is not reflected in this Frobenius norm and operator norm. To address this like orthonormal and ambiguity, we simply take the best rotation into consideration and define the distance between U and U star modulo the best rotation matrix. That means, for example, if we want to use the spectral norm, we take the minimum among all possible rotation matrix, the distance between UR and U star. Similarly, we can take the minimum Frobenius norm distance between UR and U star, where we take R to be the best possible rotation matrix. Okay. From now on, we will use those two distances. With these like preparations in place, we can now state a simple version of the famous Davis-Cohen sin theta theorem, developed by these two gentlemen, Chandler Davis and William Cohen. It states as follows. Suppose M star is positive semi-definite and has rank exactly R. If the size of the noise is smaller than the Rth eigenvalue of M star, then we know that the distance, the spectral norm distance between U and U star is not larger than a quantity shown here. Okay, so let's parse this theorem a bit. First, on the numerator, we have the size of the noise. It's quite intuitive. As the size of noise gets larger, the distance between the two subspaces will get larger. Okay. And another thing I want to remark is that the condition shown here, it says that the size of the noise should be smaller than the R's eigenvalue. It turns out that in this PSD case, the R's eigenvalue is also the difference between the R's eigenvalue and the R plus ones. That's because the R plus ones is just 0. And we usually call this one, the difference between the R1 and the R plus 1, the eigengap. Okay, so in this case, the condition here can be translated as if the size of the noise is smaller than the eigengap, then the distance between the subspaces scales somewhat linearly with respect to the size of the noise. Okay, so that's the key message behind Davis-Cohen's sin theta theorem. Now let's apply this general theorem to the stochastic block model we introduced moments ago. Recall that the key matrix we identified there was the M star matrix, which is a shifted version of the expected adjacency matrix, which is also rank 1. Okay, and the surrogate matrix M is similarly the shifted version of the observed adjacency matrix. Okay, we will use U star to denote the leading eigenvector of the population matrix M star. So it's just 1 over square root n times the 1 minus 1 vector. To be specific, here 1 is of length n over 2 and minus 1 is of length n over 2. Okay. Then we can apply the Davis-Cohen-Theta theorem to obtain the following. The L2 distance between U and U star is smaller than the quantity shown here, as long as the distance in the size of the perturbation A minus expected of A is smaller than the first eigenvalue of M star, which can be calculated as the quantity shown here. Okay, so as you can see from this simple application of Davis-Cohen, the distance L2 distance between U and U star depends crucially on the size of the perturbation, namely the spectral of A minus expected version of A. So we need to understand this quantity a bit better. Actually, and very fortunately, we can use the matrix concentration inequalities to bound or to control this operator norm. Turns out that for this SBM model, if P is larger than Q and P is order-wise larger than log n over n, then one can use matrix concentration to get the following result. With high probability, the size of A minus EA in terms of the spectral norm is no larger than square root n times P. Okay. For the sake of time, we don't have time to talk about the details of how matrix concentration inequalities will inform us of this kind of inequality. But for now, we will take this for granted. Okay. Now let's substitute this like perturbation size of the noise into the Davis-Cohen perturbation bounds. We will reach the following conclusion. The distance between the L2 distance between U and U star is no larger than square root n times P over n times P minus Q. Okay, provided that the gap between P and Q is sufficiently large. Okay. This condition can be equivalently written as P minus Q divided by square root P larger than 1 over square root n. Okay, once we satisfy this condition, then Davis-Cohen will tell us that with high probability, the L2 distance between U and U star will be smaller than 1, much smaller than 1, okay? And then since we classify nodes based on the sign of this U eigenvector, we will soon realize that this condition or this conclusion will further imply nearly perfect clustering, namely almost all the nodes in the graph are classified correctly or by the spectral methods. Okay, this is a simple algebraic exercise. You can do it on your own. So let me explain those in more details. This is the condition we have for spectral method to perform well. It means it basically says as follows: the gap between the positive probability P and the negative probability Q should be sufficiently large, and it would imply nearly perfect clustering of the spectral method. It turns out that this gap condition is information theoretically optimal, as shown in the previous work here, up to certain log factors. Both in the dense regime, that means if P and Q are on the order of 1, and in the sparse regime where P and Q are both vanishingly small, on the order of log n over n. Okay? This kind of showcases the strong performance guarantees of spectral method in terms of almost exact recovery. Okay? So now let's look at the empirical performance of spectral clustering. On the x-axis, I showed you the gap between P and Q. I call it mean difference here, delta. And on the y-axis, I showed you the empirical success rate, which is the probability we observe exact recovery of all nodes in reality. So I believe here is like over 200 Monte Carlo simulations. As you can see from the graph, once the gap between P and Q is large enough, say it's larger than 0.3, then the empirical success rate is just 1. So spectral method always return the correct classification, the correct community for every node, not just almost, but just exact recovery of spectral method. Okay, so this kind of exact recovery phenomenon cannot be simply explained by the L2 perturbation theory we just introduced, and it calls for a fine-grained analysis. But what's the fine-grained analysis we are seeking? Let's do a bit of reverse engineering. We know that spectral clustering uses the signs of the eigenvector U to cluster the nodes, okay? And that means the spectral method will achieve exact recovery if and only if the sign of Ui and the sign of U star I are the same. That's a simple conclusion or observation. And a sufficient condition for this same sign is that if the distance, the element-wise distance between u and u star is no larger than 1 over square root n, then we can guarantee that u and u star have the same sign across all the entries. Why is this? This is because u star, if you remember, every entry of u star has the magnitude exactly equal to 1 over square root n. So if u is not far away from u star, the distance is smaller than 1 over square root n, then u must have the same sign as u star in every entry. Okay. Based on this, like reverse engineering, we find out that what we need to showcase the exact recovery performance of spectral method in SPM is an L infinity perturbation bound on the eigenvectors. Okay. So this motivates us to the third part of this part, spectral method. We will introduce a fine-grained analysis. I call it L infinity perturbation bound. Okay. As before, let me set up the framework and introduce a bit of a notation. To simplify the presentation, I'm going to focus on the rank 1 case. Okay, that would suffice for us to understand the spectral method for community detection. What we have is a ground truth matrix M star. We assume it's rank 1 and positive semi-definite. Okay, so its eigendecomposition is given by lambda star times u star transpose. We introduce a new notion called incoherence, mu. Here, mu is defined to be n times the largest entry, the square of the largest entry in u star. Okay. As you can see, mu is sandwiched between 1 and n. Okay, when mu is equal to 1, let me state it reversely. When u star is just the 1 over square root n times the 1l vector, then you can compute that mu is actually 1. Okay? When u star is given by, say, the first basis vector, the E1 vector, then you can compute that mu is equal to n. So as you can see from this calculation, a smaller mu indicates that the energy in the eigenvector u star kind of spreads out across all the entries, while in the other extreme, when mu is large, the energy is quite localized. Say it's localized in the first entry. And what we observe is a perturbed version of M star. That's given by M, which is a superposition of M star plus E. Okay. And here E is a symmetric noise matrix. Since we are dealing with statistical applications, one often have some statistical structure of this noise matrix. For this general theory, we will assume the following statistical structure of the noise matrix. We assume that the lower triangular part of this noise matrix obeys the following. First, every entry has mean 0 and has bounded variance. The variance is bounded by sigma squared. In addition, the size of the noise is element-wise bounded by B. Okay. In fact, we allow this range of noise, B, to be much larger than its typical size sigma, in a sense that B could be as large as sigma times square root n, modulus on mu and log factor. Okay. With this set of notations and assumptions in place, we are now ready to state the general L infinity perturbation theory. With high probability, there exists a number z that's either 1 or minus 1, such that the element-wise difference between zu and u star is smaller than the right-hand side shown here. Okay, so let's parse this theorem a bit. First, let's consider the case where mu, the incoherence parameter, is otherwise smaller than square root log n. Then the L infinity non-bound will tell us that it's otherwise upper bounded by just sigma times square root log n over lambda star. Sigma kind of measures the size of the noise, and lambda star is the leading singular eigenvector of the matrix. Okay, if we compare this with the L2 bound we can obtain from the classical spectral analysis, we will see that the L2 error between Zu and U star is otherwise bounded by sigma times square root n over lambda star. So as you can compare here, the L infinity non-bound given by this theory can be square root n smaller than the crude L2 bound. okay, given by the previous classical analysis. This showcases the advantage of a fine-grained analysis. Okay, so now let's apply this general theory to the SBM problem. Okay, this is just to recap a bunch of notations. We have a key matrix M star, which is also a rank-1 matrix, and we have the surrogate matrix M, which is given by the shifted version of the adjacency matrix. We use U star to denote the leading eigenvector of this one, and it's the best case. Okay, we have a fairly delocalized eigenvector. Given such a model, we can simply compute that lambda star is equal to n times the gap in the probability over 2. The incoherence parameter is simply 1. The bound in the noise is, remember that the noise is the Bernoulli random matrix, so that it has bound 1. And the variance of the Bernoulli random variable is no larger than P, which is the maximum, which is also the maximum of P and Q. Okay. Given such calculations, we can apply the infinity perturbation theory. In particular, we will apply the second one to yield the following conclusion, that there exists a number z, either 1 or -1, such that z times lambda star times u is element-wise close to m times u star. And the element-wise difference is no larger than a quantity that depends on p, q, and n. Okay, you can ignore such a complex formula, and I will denote this just as delta. So operationally speaking, it means that the leading eigenvector u is quite close to a linear function of the population eigenvector u star. So as you can see from here, everything boils down to controlling the entrywise behavior of this mu star vector. Okay. Fortunately, concentration inequalities again can help us in understanding the entrywise behavior of mu star. As long as the gap between the probabilities P and Q is large enough, one can show that for the first half of the nodes, the corresponding entries in mu star is larger than a positive quantity epsilon 0. Okay. Similarly, for the remaining half of the nodes, the corresponding entries in mu star is smaller than -1 times this positive quantity epsilon 0. Okay. Without proving this, we will just state the key message out of this calculation, that is the entries in mu star, they are bounded away from 0 with a gap epsilon 0, and the bounds, the deviation from 0 has the correct sign. As you can see from here, the first half of nodes mu star is positive, for the second half of nodes mu star is negative, okay, with a gap epsilon 0. Now, with the previous two calculations, let's complete the picture and close the loop. On one hand, we know that mu star has the correct sign, okay, and it's bounded away from 0 by a gap like epsilon 0. On the other hand, we know this vector, the empirical eigenvector u, is not far away from this mu star vector in an element-wise sense. This is given by the L infinity perturbation theory, okay? And the upper bound is delta. Combining those two, we will see that as long as one can show epsilon 0 is larger than Theta, which is true by some simple linear algebra, it will naturally follow that ZUL has the same sign as U star L. Okay? Since we classified the nodes based on the sign of this UL, we soon realize that this indicates exact recovery of all the nodes of the spectral method. Okay? Now to be precise, let me state the following theorem for the spectral method for SBM. As long as the gap between P and Q is larger than 2 times 1 plus epsilon times log n over n, we know that with probability going to 1, spectral clustering will achieve exact recovery. Okay, not just almost exact recovery given by the L2 bound. It turns out that this gap condition on the probabilities is also information theoretically optimal, and it's sharp in the sense that if the left-hand side is smaller or equal to 2 times 1 minus epsilon times log n over n, then we know no method whatsoever will recover the true community structure. This indicates that spectral method is the best method for detecting communities in this simple symmetric two community SBM model. Okay, and this result could only be shown via the L infinity perturbation bounds we just introduced. Okay, so in the end, let's together take a bird's eye view of possible extensions of the spectrum method we introduced so far. And those will basically be things we don't have time to talk about in this tutorial. First, we have introduced Davis-Kahan's sin theta theorem for positive semi-definite matrices and for the leading eigenspaces. However, that's not a restriction of Davis-Kahan. In the prior literature, there exists actually a general version of Davis-Kahan that works for general symmetric matrices, not necessarily PSD1, and that works for any group of eigenvectors, not just the leading eigenvectors. Okay. In addition, in the prior literature contains a theorem called Whiting's theorem that works for the perturbation theory for singular subspaces. Okay, and this will allow us to address the matrix completion problem, where we have a singular decomposition of the key matrix M star. In addition, we have introduced the ranking problem where we have a probability transition matrix. It turns out that we also have an eigenvector perturbation for the probability transition matrix, which is an asymmetric matrix, but whose eigenvalue reveals critical information about the underlying problem. Okay. In the third part, we introduced the L infinity perturbation bound for the leading eigenvector. However, we have a general version for the leading eigenspace of the leading and singular space, not necessarily just one eigenvector, but a group of eigenvectors and a group of singular vectors. In that case, we don't measure the L infinity norm. In turn, instead we measure the L2 to infinity norm, which is the largest row norm across in the matrix. Okay, there is a general version of this that will allow us to establish finer performance guarantees, say, for example, for the low-rank matrix completion problem. All of this, you can find it in a recently wrote monograph called The Spectral Method for Data Science, a statistical perspective that's written by Yuxin, Yuejie, Chen, and myself. Okay, you can find it, I believe, on arXiv now. That's all for this part of the tutorial. Thank you all for your attention.